One person is missing, so you can admit him later on.
Yep.
Okay.
So thank you, Professor. This is the third part of our session.
Hocam ben sizleri duyamıyorum. Benim sesim geliyor mu?
Yes, I can hear you.
Peki ben bir çıkıp hemen tekrar girmeyi deneyeyim o zaman.
Okay, let's wait for you.
Evet. Duyabiliyoruz. O zaman hocam sen galiba admission yapacaksın. Olması.
Okay. So what we have here is actually plastic design. In order to bend this rebar, we have to do a plastic design. So this is plasticity. If it's elastic, I cannot do it. It will come back to where it was. It will just snap back. It has to, in order for it to stay like this is plastic design. And then in the guidelines, it says the internal bending diameter should be greater or equal to than 6 feet. And actually, in the most recent earthquake code, it is 5 feet. So then, of course, to my mind comes this question: why 5? Why 6? Where are these numbers coming from? What is the understanding? Why not 10? Why not 4? Why not 3? Why is that? And I wanted to develop or investigate a solution for that. So what is the assumption for the 6 feet? Can I bend everything on 6 feet? Or for example, for ties, it is always recommended S220 for steel ties. Why? Why S220 and why not 420? Or what happens if I do 420? Or what I need to do if I want to use 420? So these are some questions that comes to my mind. And this is something that I've looked into. So coming back to our graphs, stress strain graphs, we have the ductile material, we have the brittle material, right? So we want ductility is good. We all agree on that. So what happens at this after the maximum? We have the region necking begins. So we would rather not use this region at all because this is now the structural element is basically steel in this case, is just on the road to complete fracture. So this is our maximum, and this is the maximum that is being referred to. So yet I know that I am in this region. I take the yield line, and then I take a certain percentage of it, and then I design my whole design in this region. Why do I need to deal with this? Well, if I need to do this, I need to plastify it, and I need to be able to deform it up to these stress levels. So once I release this stress, what I had done is that I have implemented a permanent plasticity in the shape. It has become plastic. It is linear extension has increased, and I still have some more slack to go. So whatever my maximum value is, it will be a good thing to use a certain percentage of value of that for my plastic purposes. So again, many years ago, I did some sketches on my notebook, and I wanted to look into this. I was investigating what this D had to do with anything. If I want to rotate it 45 degrees, 90 degrees, 180 degrees, how does this curvature relate to stresses? And I did some simple analytical geometry about it. And then I found a correlation between the tensile strains and the level of bending. So this was my first sketch. I'm going to now portray it in a better way. Here's what we have. So this is our rebar with a diameter of phi. The DC arc is the exterior fiber. The BA one is the interior fiber, and FE is the neutral one. And I'm bending it around this mandrel. Okay? Everything okay? So my length, outer length, inner length, central length is pi r0. This is half the perimeter of a circle, pi r0. And my exterior length, which is CD, is pi re. So the elongation between the two is pi times re minus r0. My strain, in comparison to the central axis of this bent rebar, is delta over L, which is pi re minus r0 divided by pi r0. So from this one, I can say that re, the radius of the exterior edge, is r0 plus phi over 2. So now I can relate my strain to my phi and my bending radius. So I replace RE by R0 plus phi over 2 minus R0 divided by phi R0. I get epsilon, which is my strain, equal to phi divided by 2R0. If I give an allowable value to this epsilon, epsilon allowable, phi divided by 2R0, from this I can estimate what my R0 should be. R0 should be equal to phi divided by 2 times epsilon allowable. Since I want to know the internal radius of my mandrel, Ri becomes equal to phi over 2 multiplied by 1 over epsilon allowable minus 1. My internal diameter becomes phi multiplied by 1 over epsilon allowable minus 1. So here I got a mathematical sentence that correlates the internal diameter in relation to the bar that I'm trying to bend in relation to the allowable level of strain that I'm willing to impose, which is going to be somewhere here. So now let's work on this. Let's play with this. I have a very ductile steel, which is very ductile, and the allowable is 20% plastic strain. This is what I can use. In that case, my R0 becomes, according to the formula we just created, 2.5 times phi. Internal diameter, the radius will be 2 phi. Internal diameter will be 4 phi. Or just using this simple one, the internal diameter of the mandrel for this type of steel will be phi multiplied by 1 over 0.2 minus 1, 4 phi. But if this is 0.2, okay? If it's 0.12, if I have a brittle steel, something like this guy, okay, where the ductility is diminishing, if this value is not 0.20 like this, but 0.12 like that, then I'm a bit in trouble. If I use that value, 0.12, the internal mandrel diameter will be di is equal to phi times 1 over 0.12 minus 5, 7.4 phi. So if I try to bend this guy along the 6 phi that is being recommended over here, I will be in trouble, big time trouble. Does everybody agree? Because this steel does not have that level of ductility to do all this breakdowns for me. So then let's have an understanding then. Let's find a method where we can say that, hey, if this is my rebar, if this is the tensile ultimate strain level, I don't want to use it completely. I don't want to strain it up to this point, because after that necking down begins. So if this is the maximum, let's say I want to use about 80% of it. Then we can determine the bending diameter. For example, if this is a mild steel with a tensile strain, maximum tensile strain of 0.20, let's use 80%, 0.16%, 16% of the tensile capability. So according to this analytical treatment, which is nothing but simple beam bending, the internal diameter can be 5.25 phi, but this is a very soft steel. But if it increases, if I need to bend something quite brittle, I need to bend it around a bigger diameter. So when somebody recommends me something like this, the question I ask, I mean, this is not enough. Something should be written. This is for mild steel only, because why 6 phi? 6 phi is generates quite a lot of tension and quite a lot of strain, and the material should be able to respond to it. Now, the problem is, what is the problem? If I bend something, but yet it's not capable of doing that, what's going to happen is that I'm going to crack this part. I will crack it, or I will weaken it a lot. I will weaken it. And I will think that I have anchored it, but this anchorage may not work. The cross section is reduced. I am now beyond this part. And if it's a brittle material, if it's a mild steel, if I'm lucky, I may be in this part. But if it's a brittle material, I may be in this part, very close to breakage. Very close to breakage. Okay? So plastic, I need that plastic quality. And the reason, for example, now I understand that, when this table is saying that use 0.18 at least, I can bend this steel for around the mandrel of 6.5. This is what I can do. I cannot do the same thing with this. If it's 0.12, I should be very hesitant to do so. My bending diameter should be increased accordingly. So whenever we do a reinforced concrete cage design, we are doing a plastic design. Whenever we are constructing these, we are doing a plastic design, even at this stage. If I'm composing these types from S220, I can bend it at 6 feet. If the diameter is 8 millimeters, the bending radius is 24 millimeters, and I can fit it very nicely inside my beam. But if this steel is 420, then I may need to bend it around 10 phi, which is 5 times the diameter of the rebar for the radius. Then the bending radius should be 40 millimeters. So the problem with this is that I may have a difficulty fitting it inside my reinforced concrete formwork. Is everything, could I convey my discussion? Am I clear on that? Do you have any questions for our discussion? I think this will be a good time to collect any questions that you may have. Was I able to convey to you the understanding of this relationship between the plastic capability and the bending of these rebars? It is very important. Because whenever you do a reinforced concrete or a prefabricated concrete design, we do this. For heavily reinforced beams, we do this. We need to be able to bend these rebars and form our cages. And when we do our, for example, frames, we need to be able to anchor them. And we need to be sure that this anchorage will work. Because if this anchorage will break, then it is no good at all. For example, over here, we have the tension at the top, tension at the bottom here. So we have this transition for the tensile region. So this requires some heavy rebar formation. And the rebar must be capable of doing this. And this internal bending diameters is very important. Because if it's brittle steel, we cannot be ignorant of that fact. Because how these frames will function under the vertical dead loads or under the lateral loads, how they will function is correlated to that. So this joint should be able to work. But if we have provided some form of a crack at this point, something that's not holding together very nicely, it will fail from this region. And these, my friends, is the plastic design. This is plastic design right here. When we purchase our reinforcement, we need to be extremely cautious about this plastic capability, because metallurgically, steel producers, providing this part isn't a problem. Providing this parts, it yields at 220. Oh my God, good for you. That's not a problem at all. Providing this part is the problem. Because this ductility is only achieved by purity. And achieving purity is cost. So if it's a cheap steel producer, they will probably try to forfeit with this cost and provide you with brittle steel. And just by looking at where it yields, right, this is the only value that you use for design, don't feel happy. This is the part that you will need eventually. And this is the part that is going to cost you. And this is the part, actually, especially when they export their items, sometimes some good quality materials are always exported outside, but sometimes cheap materials are unfortunately held in the country. Why? Because we need to have that ductility. My friends, this ductility is very important. And this is achieved by purity. If the steel has a lot of foreign agents, this ductile behavior will be jeopardized, and it will eventually affect your design. And this is my recommendation and my train of thoughts between the bending radius and ductility and how we use them in our design. So in conclusion, seismicity is a natural quality of our world. It is not a random act of punishment. It is not a surprise. We must understand it and understand its effects. We must design properly against these effects, and ductility is an important quality of material and structural behavior. And that ductility must be implemented in design generously. It cannot be gambled with seismicity. The ideologies of load and resistance factor design and performance-based design must be thoroughly understood and properly applied. Because sometimes when we say energy absorption, right? This is a very clean word, two words, energy absorption, right? Well, if you have an explicit response to that, like a damper, a friction pendulum, energy absorber, whatever, then fine. But if you are just constructing your reinforced concrete and you are talking about energy absorption, you are talking about concrete cracking. You are talking about destruction. Because energy absorption, you know, it is a very sweet word, right? Energy absorption, like I absorbed energy. How do you absorb the energy? By cracking. That's how you absorb the energy. Your building will not look like the same after it absorbs that energy. So unless, because this energy absorption was a word specifically used for explicit passive dampers and isolation systems. That's what it was reserved for. But then we transferred these two words to ordinary design and construction. So when something is energy absorbing, something is cracking, something is yielding big time. You must be aware of this. When misunderstood and improperly applied, these ideologies are dangerous. And the cost of a structure is much less compared to the added value it will bring through the life that will flourish inside that structure. And the structure must remain safe and habitable throughout its service life. So, Professor Yalçın and dear students, thank you for your presence. Thank you for your invitation. This is the end of my presentation. I am prepared to receive your questions. Thank you.
Thank you very much. I think we had 3 sessions, but 3 exciting sessions. So I'm sure some of us have some questions. I do have some questions. I mean, at least maybe 1 or 2. But I'd like to see if our students would like to ask some questions or some comments, maybe, to sort of perhaps they can sort of enlighten us with their own experiences, if they do have. So please feel free to ask questions or make some comments.
Hocam, can I ask a question?
Sure, go ahead, please. Sure.
Öncelikle ağzınıza sağlık. Çok teşekkürler.
Ben teşekkür ederim.
Presentation için. You said the structures must be designed in elastic zone, not plastic zones, and we do not crack our structures, and we don't need to demolish after the earthquakes, right?
Yes.
And so, do you think this is economical? Because in the recent earthquake, so buildings which has been built by the code does not collapse, and the earthquake, after earthquake, most of them does not yield so much. So don't you think we are successful in this design philosophy?
I don't have a statistic regarding that, you know, the buildings that has been designed according to the codes have collapsed or have not collapsed. I don't have that statistic. And when I say that elastic design, yes, I do support that. And the level of plasticity that can be experienced by a structure should be limited. My suggestion is that, for example, I don't know if you have seen the interior views of some of the structures from inside that have survived. Most of their in-building walls, non-structural walls, and sometimes structural elements were damaged. The building was yes, the building didn't collapse, but yet it was no longer habitable. Now, in a country such as ours, you know, we are not living in a country where earthquakes are, or this magnitude is experienced like once in a lifetime. It's quite frequent. My suggestion is that, we should not refer to them as rare events, but as events that actually occur quite often. And yes, of course, if it responds elastically, or if we isolate that structure from the ground, there will be some cost items, for sure. But, when I look at the cost items of constructing a structure, sometimes we spend a lot of money for decoration or for functional additions to the building, which can be actually used for more structural purposes. Because our structures are heavy, heavier than they should be. There's a lot of added weight to our structures that is not beneficial to the structure at all. Some types of floorings and the marbles that they use and all the cosmetic stuff, which are quite expensive too, Some interesting facade work, because passive energy dissipators, seismic isolation, or providing a bit more strength, a bit more elastic response to fundamental structural load carrying capabilities of structure, they are not that costly as one would imagine, or as one would have it understood. It is not like quadrupling the cost of a structure. But unfortunately, like in our country, construction industry is a major economic force. So such being the case, in order to have many people be able to buy stuff and also generate this economy, sometimes I'm suspecting that some decisions are being made which are not naturally safe. Because, when you say that at the extreme events, the structure will not fail, but it will not be habitable, is a very dramatic thing to say. Because, for people living in Istanbul, when is that going? We are going to live that, right? If we were to buy a house now, within a certain amount of years, there's an expected earthquake. And we are buying that huge house with huge amounts of money, knowing that it will likely be damaged beyond recognition once the earthquake hits, but I'm alive. When spending that type of money, that structure can be designed in many other forms and fashions, where the major cost of the structure is structural cost and less amount of money spent on architectural costs. So this is my point of view, because when we say that energy absorbing and not damaged and this and that, these are very fine things to say, but when we see the pictures of the building that hasn't collapsed but been damaged, is like some bomb exploded inside the building. And I don't think that is fair. I don't think that is fair. This is not something that I would want to pay for if I knew about it. If I knew about it, I mean, as the people knew about this is something that they will object to.
I agree with Professor Bezgin's view, and I also just quickly want to add that there's also sustainability aspects to it, right? Like in the 21st century, we cannot be just building things and demolishing them and rebuilding them. It's just not feasible. So,
Yeah.
Another valid point.
So, I would like to ask another question. So, in Turkey, we use prefabricated structures, especially in industrial buildings, but we do not use usually in residential areas. I don't know if it's popular in the United States, but do you recommend that prefabricated structures in residential areas? Because in situ buildings is not reliable because of the applications and different kind of concrete pouring and reinforcement structures. So do you recommend and do you think we can use prefabricated structures in residential areas in Turkey?
I mean, I certainly do, but I just don't agree with one aspect of what you said. Cast in place is a wonderful method of production. If done right, there's no problem with that. Prefabrication, of course, prefabrication.
I know, but not reliable.
No, let's not compare it like that, because truly, I mean, cast in place industry has also responded very well to the contemporary demands of construction. These are just methods, but prefabrication is something, yes, it's something that can be done elsewhere and then assembled on site. So it has certain benefits, right? Certainly it does have benefits. And as I said, I mean, the buildings in Turkey are very heavy, heavier than they should be. And the majority of this weight is non-structural. It's like fat, body fat. It has a mass, but it is not structural. It should be more muscle. I mean, if you look at the buildings in the United States, in Canada, in Europe, new buildings, they are lighter weights and more muscle. But in our structures, they're like heavy. The interior walls are like those bricks and, you know, plasters all over. We make floorings and heavy, everything heavy. It should be a bit more simple and lighter weight. There's no need to make it that heavy, and prefabrication, of course, can respond to our needs in very good ways. But there needs to be a consensus, and also, of course, you know, all the constructors. There are too many contractors in Turkey, too many people in this business. Anybody who has enough money can get into this business and do things as they like and spend money on things that we don't need, actually we don't want, right? Nobody's asking. We are being offered certain things and we select from them. But sometimes, you know, I go into this building, I look at it, I see all this, you know, delicate materials. Like, I don't want to spend my money on that. Who asked me that? I mean, just because it was supplied, I choose from that, but it is not my demand. So I think things can be made lighter. And when things are made lighter, actually, this elastic movement becomes more possible. Less forces are pulled upon. And if we construct in the correct places, and of course, you know, housing should not be like an economic demand. You know, if you look at it as an economic force, you know, we need to construct this many housing units and the economy will, so that it will carry on. This should not be a political agenda. I mean, a country should have different industries. Construction industry, a country should not be based upon a construction industry. Construction is something that must be done once, and it should last for a couple of generations at the least. You know, a building should last. Why, you know, why low lives? Why is that? Why low service lives? Why is that? A couple of generations, 1 generation, 2 generations should be possible. I don't want to keep on buying things and demolishing things and making things. No. That is actually a very what I have to say, like a kısır döngü, the English one didn't came to my mind now. We have to get out of this loop. Because for countries like us, unfortunately, construction is the main business. And in order to keep the business alive, we cannot keep on doing what we are doing like right now. And yeah, if you want to isolate the structures, yes, please do so by all means. If you want to absorb the energies, please do so. Please provide passive energy absorbers here and there. You know, absorb that energy. I have no problem with that. But don't construct something and talk about energy absorption. And energy absorption means actually cracking and collapse. That's what I'm saying. That's my point of view on that.
Thank
and
you.
yes, just because of this, you know, sometimes some people will go out of business because some industries will eventually die. The brick producers will go out of business in order to make things lighter weight. And not everybody may be able to buy the houses. But then there's different forms of construction, different forms of materials. There are wood houses. There are lightweight steel houses. There are cold form steel houses. Why does it have to be this massive concrete houses all the time? So I think we need to address these issues as well. But more weight does not mean much, and this more weight is actually what is hurting us in this aspect. Thank you.
I had a question. Sorry, I had a question regarding your comments on how we should make it lighter, the structures. What are your thoughts on the usage of fiber reinforced polymers or composites of polymers, as they are used a lot in the aerospace industry to make structures lighter, like aircraft? Do you imagine that kind of technology, fiber reinforced polymers, or
I do imagine.
a textile reinforced polymers, like bridges out of them?
Yeah, for facades, especially to make lighter weight facades, actually fiber reinforced concrete that can be as thin as 10 millimeters, and we have used them and we have constructed them. fiber reinforcement certainly makes it lighter weight, and it opens up various possibilities in construction. So yeah, advancement in materials can be implemented and applied. But sometimes resistance is given to these new developments because not everybody can apply, and so it takes some time for the new methodology to find an application in the industry.
Okay, thank you.
Thank you.
Very, very good. Actually, we're about to finish, but I just have one comment that you mentioned about the load path. The load
Yes.
path is vitally important for all structures, and I think all engineers should understand how the loads flow from one end to the other, and there is nothing sort of is lost. So we must understand the load flow mechanism when we think about the structural system. So this is one important aspect which you mentioned. Thank you.
Thank you.
And another thing is that, of course, the design of corbels, you had some experimental results. You showed us some experimental results, and one of them, in fact, I have that the second picture, I think, the deep beam picture I had in my notes in terms of I prepared them for strut and tie method. So I think that type of design, I mean, you can either carry out finite element analysis, of course, that's one way of doing it. But unlike bendable structures, one easy way of designing deep beams or corbels or you know deep sort of simple beams, one has to use, I think, the strut and tie method, which is a very powerful method to use. I'm not sure if our students are aware of it, but maybe you should check the strut and tie method for the deep beam analysis. It's a lot easier than finite element analysis because you can do it manually, which is very fine and quite powerful. So those are the two things that I wanted to mention. And one other thing is that, of course, you want to last our buildings forever, or not maybe forever, maybe 2 generations or so. Of course, there is no such thing like forever unless you build pyramids. Still, there's going to be some wear and tear if you don't have
Sure.
any clicks. So durability, I think, is one thing that we have to take care of. We have to have like a durable buildings. We have to isolate the buildings from environmental effects. Isolation, not by means of earthquake isolation, dynamic isolation, but let's say rain isolation, for instance, humidity. These things are really, the issue in all buildings I visit. I've seen corrosion problems. I've seen all kinds of problems. So those are the problems which we have, even if you don't have earthquakes. So therefore, when you buy a new building, I'm not sure if you can sort of see these things. But, like ourselves or like our cars, when people buy buildings, they say, okay, I bought this, I paid this money, and I'll forget about it. And they'll never sort of go back and then do some work. So you have to, of course, provide durability. Durability is the key. Of course, earthquakes, we have some, we allow some little cracks. I mean, otherwise, our friend said it's going to be quite costly. So probably we can allow some minor retainable work after the earthquake, but of course, no heavy damage. So those are my comments.
Thank you.
So if you have any final words, please do so. We have 3 minutes almost, so the floor is yours.
Thank you for your invitation, and thank you for giving me this chance to present to this wonderful audience. Thank you for your hospitality.
Well, we thank you and hope to see you again, hopefully some other time.
Most certainly. Thank you.
Evet arkadaşlar, bu session'da bugün bitti. Dolu dolu yaptık. Bayağı güzel bir prezentasyondu. Soru cevaplar da iyiydi. En azından bu ne kadar bükülüyor, ne kadar diameter olduğunu ben de öğrendim. Aslında güzel bir konu, enteresan. Yani bir orada kullanıyoruz galiba. %20'lere kadar gidiyoruz veya 15'lere kadar gidiyoruz. Çünkü design bizim çok limited bir yerdeyiz yani biz design'da. O da güzel bir bilgiydi. Teşekkür ediyoruz geldiğiniz için.
Ben teşekkür ederim.
Çok sağ olun her şey için. O zaman biz ayrılalım arkadaşlar. Haftaya yine online yapacağız. Bir başka öğretim üyesi arkadaşımızı çağıracağım. Bakalım şu anda aklımda birkaç kişi var ama önce bir düşüneyim. Ama online yapacağız. Haftaya yine saat 4'te buluşalım Zoom'da.
Görüşmek üzere hocam. Hayırlı akşamlar.